Okay. Thanks, Yisheng. And let me thank CITA and Rene, who is not around, I guess. Yeah. My talk has two parts. One is introducing this model, UberGravity, which is a theory part, and then I will try to do the cosmology in this context. So let me go for a brief kind of introduction. It's the way that I think we do science. We go for theory first, and then just go for theoretical consistency for our models, for example. Then we go for observations. And here in cosmology, we look at the sky. So as an example for gravity, we have this Einstein-Hilbert action, which is consistent, which describes a massless spin-2 particle without any theoretical inconsistency. And then we check the model. As an example, deflection of light by the sun. So it's the way we do physics. Then there is a problem in theory side, for example. The cosmological constant problem, which is a fine-tuning problem. We know that there is a density, vacuum energy density from particle physics, which is much, much higher than what we observed. So there is a fine-tuning problem in the theory side. And as far as I know, it's unsolved yet. But then we have some observations. We know that we are in late time acceleration. So the universe is accelerating with a positive acceleration. So GR cannot explain that. But then we modify the theory by adding a cosmological constant. And this is our standard model of cosmology. So we have this lambda, which is dark energy, and then called dark matter as a matter part, the main part of matter field. But it's not the end of the story, because then we could ask ourselves that about the new observations, or other problems in theory side. I told you about the cosmological constant problem, but there are few tensions between the prediction of lambda CDM and the observations. One is H0 tension that I will describe, and it's on the background level. The other one is sigma 8 tension, which I will give you one slide or more. It's about linear perturbation theory, when you do linear perturbation. And there are two more, void phenomenon and missing satellite problem, that maybe they are in nonlinear regime of lambda CDM. So what they say, in principle, we observe something that we cannot address by our standard model of cosmology. In the theory side, another question that I like to mention is this question that why GR should govern our gravity force. I mean, let me remind you a phrase by Einstein, that what really interests me is whether God had any choice in the creation of the world or not. So it's a question, and for me, it's not just a philosophical question. We have a lot of different types of modified gravity, and why GR is so unique. So let me say, it's a real story. At the first day, God asked for a model of gravity because he or she wanted to run a simulation, which is our universe in principle. Then philosophers, thinkers, they were discussing, and they brought a lot of models. It's the models. It's like, actually, it is by Tessa Baker. So it's what we have in modified gravity. We have different types of modified gravity. In principle, all of them are theoretically consistent. You have this stringy side, this higher dimensional inspired modified gravity, these non-local gravities, harder gravities, F of R models. This one, which became very popular recently, massive gravity and bigravity, the famous scalar tensor models, or even tensor vector scalar, and so on. So for me, the question is why nature didn't pick, let's say, Klein or DGP. My idea to solve that question is just taking average. So in principle, it is the idea. It's a question. Let me recall again the question. That did we have any choice to describe nature by another model, by another theory, or not? If you say no, we didn't have any choice, then you should say why GR is unique. And if you say yes, then you should answer to this question, that how you can do that. If the universe allows us to have more different types of gravity models, then how we can check that? And you have third option, that it's not a well-defined question. Okay, but we can talk about it later, because I talked with my colleagues from philosophy department, and after 1 week they just said, what was the question? So it's a bit tricky. My answer to this question is yes and no, in the sense that yes, we should use all the theoretically consistent models, but then at the end, because we take the average over all of them, we reach to one model. So we work with one model which is average over all the previous models. Okay. The idea is based on this paper, but then for a similar idea, you can go for Arkani Hamed et al. Paper. The name on archive version, the name is N-naturalness. They have the same idea in particle physics, and they want to solve the hierarchy problem. They say, let's assume we have different types of a standard model of particle physics, and each model is labeled by Higgs mass, so they have different Higgs masses. Okay. But I'm doing the idea in the gravity sector. So it's the idea. Let's say we have this model space which contains all the consistent model of gravity, theoretically consistent model of gravity, and then we go for an average over all these models. So it's in abstract way, actually. But then I need a probability, because I associate a probability to each model. So it's a weighted averaging procedure. And inspired by a path integral, and yes, please.
Can I ask what is the meaning of consistent here?
In theory side, if there is no instability, there is no ghost, I say it is consistent.
Okay. So there's nothing to do with observation.
No, yes, it's just pure theoretical, yeah. Yes.
So just very basic question, but what about the idea that we should use the simplest model rather than averaging over all possible models? But the Occam's razor thing, that you should just take whichever simplest model fits the data?
Yes. That one is a solution. I mean, but then you should give me a definite definition for the simplest one. Because, for example, even in gravity, when we work with metric, then Ricci scalar is much easier, no? Is the simplest one. But I'm not sure if you work with, let's say, tetrad formalism, if it is the simplest one or not. I mean,
it's defined by how many free parameters there are, I guess, right?
Yes, but then if you go for GR, for example, you cannot explain late time acceleration. You add a lambda, and if you just count this number of free parameters, then there is a conjecture. I mean, there is a model, non-local gravity model, which has one additional parameter, free parameter. I mean, same as lambda CDM. Instead of lambda, they have another term. So the number of parameters are same, and they claim that it fits with data. So then you need to choose between those two.
Sure, but in your ensemble average, you're thinking of having models that have many more, say, than this one extra free parameter.
Okay.
Right?
Yeah. Yes.
Okay.
In principle, yes. But then, for the example, I just keep going for the simplest scenario, because I will let you know in a few slides. Yeah. So this Lagrangian, okay, these Lagrangians are the Lagrangians in my model space, and I associate this kind of probability. It's a question, why this probability? It's just inspired by path integral. It's very similar to e to the minus s or e to the minus beta h in thermodynamics. Okay, but here it's Lagrangian. This one is normalization factor, and you can see I need one free parameter here, beta. As an example, I started with with higher order gravity models, and in higher order gravity models in 4 dimensions, we have 2 non-trivial terms, Ricci scalar and Gauss-Bonnet. Then you can get this Lagrangian. Okay. This is in family of F of R and G models, and it's nice because it can satisfy the consistency relation for F of R and G models. It's like this. There is a relation which is not trivial. Sorry, I'm not sure if you can see this or not, but it is F comma RR, derivative with respect to R, times F comma GG minus F comma RG squared should be 0 if you don't want to have ghost.
What is that?
F is this function, F of R and G. So usually people, when you go to literature, they are saying that we go for F of R plus G or F of G plus R. That trivially satisfy that equation, that relation. But this model non-trivially, I mean, R and G are everywhere together, and but this model can satisfy that relation. So this one is safe in the sense that there is no instability for this model. So, but yeah.
So the normalization often makes sense when we're considering some kind of, some probabilities here. But at the level of the Lagrange density, what's the motivation for normalizing this overall normalization factor?
Because, here, for me, the philosophy was like this. Each model can be there with a probability. So for me, it is a kind of probability.
Okay, so you're just trying to make sure you multiply each piece of the Lagrange by some kind of probability or probability density.
Yes, and
then it has to be normalized.
yes, and I can say one.
Shouldn't it be normalized by the integral over all the probabilities rather than
Yes, but then because it is discrete.
parameters of the field variables as well as right? You're not normalizing the actual Lagrangian, you're normalizing the Lagrange density locally by the sum, which seems like there's 2 options there, I guess.
I agree. You could go for normalizing, taking the average over here, actually, over all the fields, like what we do in quantum field theory. Yeah, I agree. But I can say one thing about here. You could go for partition function, like e to the minus beta, let's say. Okay, I am just one step ahead. Let me show you the next slide, and then I come back to this one. Sorry.
I guess Aaron's question was more like, why is the choice discrete instead of continuous?
You could go for a continuous one, but here my model space has just 2 model. So for this alpha, if Gauss-Bonnet is a model, if it is a consistent model, then alpha G, alpha Gauss-Bonnet, alpha times Gauss-Bonnet is a model too. So it doesn't change. If you mean if I should take average over alphas?
No, that's a separate question. So, but it's related. I guess my question is, if you considered, for example, the Lagrangian rather than Lagrange density, or the action rather than Lagrange density, you integrate over the field variables as well, then that might be a different way to normalize. Then it's just a number that can drop out. So it's just, this seems like a more complicated way of adding them all together. So I was just curious what the reasoning was for summing in the individual terms the Lagrange densities as your normalizing factor. That's all.
If I go for action, if I put same as path integral, quantum field theory path integral, e to the minus action, then that one is highly non-local. Because I should take average, it should take integral over d4x, over whole space-time. So it's highly non-local. So I just wanted to skip non-locality. But maybe that one is that can be an idea, because there are some papers that they go for action. It's not the same idea, but they just have they times action to the action. So in the equation of motion, they have these non-local terms. But then here you can ask something. If I start with R and G, two models, and if I give you some other model, which is theoretically consistent, so I should put this model back to the model space and do the same procedure. For this reason, I generalized the idea for these models. I go for the all analytic f of R models. And one basis is R to n. Okay? If you do that, you go for this Lagrangian, because R to the n is this Lagrangian. This one is the probability. Just one thing, that R bar is defined as R over R naught to make it dimensionless. Then this exponent is dimensionless. It is the point that you mentioned, because I could use R naught, different R naughts for different f of R in principle. So I could have infinite free parameter, but here I just go for one parameter, one additional parameter. So this model has two parameters, beta and R naught. And one thing that thing that I wanted to say, if you go for this kind of, let's say, it's partition function, it's very similar to partition function, then the Lagrangian here is very similar to free energy for this partition function. So automatically you get this factor in the denominator. This Lagrangian has some nice properties. First of all, this blue solid line is that Lagrangian. This dashed line is pure GR, pure Einstein-Hilbert, and you can see there are some modification at the infrared scale. Their higher curvature is here, so the low curvature is there. And there are some universal, I say universal, and I will let you know that what does it mean for me, properties. One, at large curvatures, it's just GR. And you can mathematically prove that. There is a region here, intermediate region, that this gravity is a little bit stronger. But then these two parts is more interesting for me. Gravity is 0 below R naught. And you have this jump. And you can show that this universal, it means it doesn't, these four properties don't depend on beta, and they don't depend on the choice of the basis. So I started with R squared, R cubed, but you could say I go for R plus R cubed plus R to 5 or something. You have some deviation from this part, in this part, but it's always up, and you get these three parts exactly the same. So in this sense, they are universal for me. And even if you put back this Lagrangian into the first, into the f of R models, and you do the same, you get the same results. So somehow I can say it's a fixed point in the space, in the model space, based on my assumption, that kind of probability and this analytic functions of f of R and so on. But then it's a fixed point, yeah.
Can you go back to the last slide? Because I'm question about normalization again. Sorry. So, if I remember correctly, overall constant we find the Lagrangian doesn't change the classical equation of motion.
Yes.
So if I go look at your equation, I don't think you have two free terms, you have only one, because beta always comes with R naught. I can multiply entirely by beta. On the left-hand side, doesn't change the equation of motion. On the right-hand side, I combine every beta with R.
Yeah, I don't think so, because it's Rn. So I have a term like beta R and beta R squared. So.
Okay.
Yep.
You're right.
So,
yes.
For the next slide, so this prediction then, I guess, the statement would be that at some curvature scale larger than the size of the universe, gravity turns off entirely. Does that have any immediate implications on cosmology in this model?
Yes, actually it is what I am going to talk about. Yes, exactly. It's a good point. So it says there is one minimum for curvature in some sense. And we can guess because we, in our current situation of the universe, we have this lambda everywhere. So we can guess that maybe this R naught is our lambda. So just one point in the theory part. This Lagrangian has the same structure like this blue line, okay? So let me concentrate on this part. This Rn, if n goes to infinity, gives you the same behavior. And you can see if this one is the equation of motion, actually trace of equation of motion for this part. And then if you go for looking for R constant solutions, you can skip this term and you get this one, this relation. And it's interesting because it says if n goes to infinity, then this part going to 1. And it doesn't depend on the value of t. So it says for any kind of energy momentum tensor, trace of energy momentum tensor, you get R equals R naught. Okay? So then maybe, I should say, because this result is based on this assumption that there is no matter field, and okay, except vacuum expectation, vacuum energy density. So it doesn't solve cosmological constant problem, but maybe it gives some hints that maybe the solution for cosmological constant problem is something like this. The gravity is not sensitive to the value of vacuum energy. And we don't need to go for, because for example, in supersymmetry, we go for vanishing, we have this superparticles for each particle, fermion and boson, so we get zero energy momentum, energy density for vacuum. But maybe it is not the solution. The solution is something like that, that gravity sector is not sensitive to the energy momentum tensor at all, for some scales, for sure. Let me just skip this one. So, it's my first slide of the second part of the talk. Let's say we have this model, which I named UberGravity. And we have these tensions. Let's see if we can say something about these tensions. So it's the cosmology part. And this part has been done with my collaborator, Shant Bahram, who is a faculty member at Sharif University of Technology. This plot is trace of equation of motion for that f of r, that UberGravity. This blue line, and this dashed line, yellow line, is minus Ricci scalar, which is the trace of G mu nu, Einstein tensor. Okay? You can see something nice here. So this one is a trace, and this one, let's say, it's just trace of energy momentum tensor. If rho, energy density of matter, is greater than a critical density, you always see gravity behaves like GR. And then there is a critical density. And below that, this model gives you just R equals R naught solution. So here you have pure de Sitter in principle. Here you have just a standard GR. So based on this observation, we suggested a model for cosmology that for energy density less than critical density, we have pure de Sitter, and for greater than a critical density, we have GR and lambda CDM. And we name it either lambda or CDM because we don't have both together. Okay. So H naught tension. I have this plot from Rachel Beaton. You can see the observations from high redshift, the CMB, for H naught gives us a value like this here. And from local measurements from supernovae, we get results from here. the result for H naught is here. So we can see there is a tension between these two measurements. Actually, it is between 2, 3 sigma. You can say it is just systematic, or you can say it has a physics. And a recent, last year paper by Adam Rees, they confirmed that they tried to take care of all the systematics, everything, and then they just reported that there is a tension. There is still a tension between these two measurements. Let's see what our model can say about H naught. We can write the Friedman equation in this, the background Friedman equation for our model. For a redshift less than a transition redshift, we have this constant H, which is this pure de Sitter phase. Otherwise, we have this pure CDM phase. Yes, and we have this Comoving distance definition. So if if your object is in a redshift higher than transition redshift, we have this part from Comoving distance in addition to this very simple part, which is pure de Sitter part. And if we go for the best fit of our model, because we had to, okay, we have this 3 parameter here, Z plus, we have this H naught, and we have this omega plus. We have one more parameter compared to lambda CDM. This one is from matter field. This one is Hubble constant. This one is the transition redshift. And I don't have a slide here to show you, but Z plus and H naught can be written as functions of R naught and beta in the original model. Okay? Here we fix, yes.
Discontinuity in the expansion rate at C equals C?
Yes.
Plus?
Z, yes, Z plus, let's say Z plus. Yes, there is a discontinuity there. Okay, I have to say something. Here we fixed H naught by Rees et al. Measurement. So it is fixed by local measurement. So in principle, it means that we already predict that local measurement is correct. Our model is consistent with local measurement. Not it's correct. It's not correct. I don't know if it's correct or not. Okay, so we go for best fit for Z plus and omega plus, and we get this one. You can see if we have BAO and first peak of CMB, because the distance of CMB toward us is a quantity which is a background quantity. So, and that one is very important. It's just one data point, but it's very small, and because it's very far from us, it kills all the degeneracy actually. So we always have this CMB peak. And if we go just for BAO measurements, we get this bigger 2 sigma region. And if we add supernovae, we have this smaller one. And to be honest, we have this kind of line, and it's not surprising because in a standard lambda CDM, for flat lambda CDM, we have the same behavior. And we guess it's because of flatness of the universe. Because if you go to the papers, if you assume, because I guess flatness, if I'm correct, flatness, if you look at the, I don't have the plot here, but in Planck's paper, they showed that if you assume the flatness, the flat universe, then it kills a lot of degeneracy. So it gives you a kind of line. We think that it's because we also assume that we are in a flat universe. So there is a best fit for that. And then if I draw the Comoving distance, you get something like this. It seems that for this region, for redshift around 2, these two BAO are coming from this, what is the name of the, I forgot the name. Okay, the Lyman alpha measurements. So it seems there is a tension between these two data point and lambda CDM. We have the same tension, but we are below these data points. But the interesting part is that we go back up, and then we can get L peak at 301, which is at 301, we get at 301. So for L peak, it's okay, yes, please.
So should I be able to see a kink here in this red dash curve at 0.45?
Exactly, yes.
Okay, you just can't quite see it, but I'll just
Yes.
see this there.
No, yes, it is there, yeah.
Okay.
Yeah, I can show you
Okay.
the more zoom in one
Sure.
afterwards, yeah.
Sorry, you said you assume a flat, you were assuming before the transition, right?
Yes.
And the transition will consider?
Yes. Yes. Oh, no, sorry, not flat. Both are flat. Yes, they are spatially flat. Spatially flat, yeah. Okay, so it's kind of conclusion. Here I should say something that we don't say that we can solve the tension, because now we need to take care of the perturbation and the constraints in perturbation. Our chi-squares are very similar to lambda CDM chi-square, but what we say is that it seems it's a suggestion that if this H naught tension is physics, maybe the universe switched to another kind of cosmology at lower redshifts. And this model, UberGravity, gives us this chance for this switching. And I should say, there is a discontinuity, as you mentioned, but then we can go for a more continuous scenario too. So let's say we talked about H naught tension. Now, let me say a few words about sigma 8 tension. The tension is, this one is Planck data. So it's early universe data. This one is late time universe data. So you can see that sigma 8 does not match. This one from Planck. And recent DES paper, they say they reduce the tension, but you can see that there is a tension. There is still a tension. It's not too big, but it seems there is a tension between high redshift and low redshift measurements. So this sigma 8 is at the level of background, at the level of linear perturbation theory for cosmology. So we do the same. We say we have this total energy density, and then this one is the background part, this one is the linear part. Then we just check that if it is below or above this critical density. And you can imagine that what happens, because this part, this linear part, depends on K, so touching this critical density depends on the mode, on the wave number. And this one is plot. At redshift, these solid lines are lambda CDM. This one is the power spectrum. This axis. This one is wave number K. Solid lines are lambda CDM at different redshift 2, 1, and 0. And dashed line are this model, UberGravity model. At redshift 2, they are on top of each other, as we could guess. Because at redshift 2, lambda CDM is in very CDM dominated era, and our model is in pure CDM. So they should be same. But when we arrive around Z1, let's say, we predict more power compared to lambda CDM. And this one is understandable too, because the transition redshift was at 0.45, yeah, 0.5. So for us, we are in our model at redshift 1, we are in pure CDM scenario. But in lambda CDM, already lambda plays some role, even if it's small, some friction. Okay? So it gives some friction. So they have less power. Our model has more power here. But when we get to Z equals 0, the present time, we get less power for lower Ks. And the reason is When a mode touches the critical density, then it doesn't grow anymore. But in lambda CDM, because even now we have 30% dark matter, it grows a little bit. And just two scales, this scale is around 0.2 is nonlinear scale, so we don't trust to our model at this regime. This one is sigma 8 scale. So you can see we have less power below sigma 8 scale. Okay? At the first look, it seems that it is in the correct direction because we predict less power for sigma 8. But I should say, we cannot trust to this result because of a reason. If you look at these solid lines, you can see at different redshifts, the shape doesn't change. Because in lambda CDM, the growth of matter field doesn't depend on K. So it's just an amplitude. But for our case, we depend, I mean, the growth factor depends on the K. So we get a K-dependent, a scale-dependent matter power spectrum. So what does it mean? It means we should go back to this data, because these data for lambda CDM, it's not important if the data is at 0.3, redshift 0.3 or 0.5. They just stack all the data with this power spectrum here. And because the shapes are same as each other, it's very easy for them. But for us, we should go back and then see the data that made this problem, this sigma 8 tension, are from which redshift, and do reanalyze everything from scratch. So we don't know if it solves a sigma 8 or not. But for sure, this model predicts a scale-dependent matter power spectrum. And here, no, not. So I told you a few words about sigma 8 tension, and it's it for now. We could go for nonlinear regime, but at this moment we don't have any calculation for that. So let me just stop here. Thank you.
Questions?
At CITA, we've been, oh, by the way, welcome, Marcy is opening.
Yeah, thank you. Very nice to meet you.
We have quite a little exercise going on. We like to refer to it more like coupled dark energy because we go into the Einstein frame, which is a bit more awkward to do with the specific assumption we have. But all of the effects you're describing are involved that we're treating in terms of the effect of critical density. It appears in any, most manifest, I think, in the Einstein frame, because the way people have been doing the Jordan frame in terms of tests is actually, I think, like somewhat flawed, because they draw time-dependent. We've been exploring this, and one of the critical things we've been doing with my friend next to me here is going into the nonlinear regime. So the central issue that we are not treating quite properly, and I think that you get around it by your sharp cut, is screening.
Yes.
So effectively, you have an on-off switch to screening,
Yes.
which is completely density dependent rather than being a transition. In essentially every modified gravity model that's being used, there is a transition regime. We don't think it's that important in terms of what we've been doing in the Einstein frame. So from our perspective, we're doing, we don't call them Uber models, they're just coupled dark energy or modified gravity models. But we are trying to do Bayesian constraints of various parameters for that and in various regimes, and that's been going on for a while. So I'm relatively sold by the possibility, if not, I mean, you know, one of the problems is who ordered the parameters, but I think it's a very reasonable approach to be taken.
Yes, I mean, yes, it seems that we have a kind of screening, depending on the critical density. I agree.
Well, your screening has no fuzziness associated with it. It's a sharp screen.
Yes, yes, I agree.
So, which we think we're hoping it's a pretty good approximation because it's probably a reasonable approximation in spherical models, but the key to our nonlinearity are ellipsoidal collapsing models for objects, and that's not as clear. There are other tests that can be done, and it's only for some class of cosmic objects where you would see in the sort of far field of the objects by the profiles of the density structure around them, you would actually get evidence for the transition region. And so there are other ways to try and go after this phenomenon rather than just to do some global CMB plus LSS analysis in a linear regime. What you are primarily doing because the other part is a lot harder.
Maybe I need to have a look at your works. Then, I mean, and the other thing that you said that if we go to Einstein frame.
Well, yeah, I think with your case, because of the conformal transformation would look a little awkward.
Yes, it is actually.
Because essentially you send m Planck squared equal to 0 at below some critical density, and so I'm not sure exactly how that would look. I don't actually. It may well be that you can't do it, or I don't know. Maybe somebody is agrees with this, but the conformal transformation would be a bit weird in that discontinuity case.
Yes, actually we can show that if you do this conformal transformation to go to Einstein frame, that region, that R naught region. Okay, that R naught region, the conformal factor going to 0. So it means you decouple the gravity sector from the matter sector.
Yeah, I think that's probably true. See, the key thing in what we're doing is that below a certain in the Einstein frame, below a certain density, the cold dark matter particles would actually have changing masses. And then they get into the saturated asymptotic regime, which corresponds to your CDM regime above a certain density. And so in your case, I don't know exactly what it would mean for the equivalent of the dark matter particles changing in time. I'm not sure. Or if it could even be looked at that way.
Yeah.
It probably
Yes.
can.
Yes, maybe. The point here is that because we have this disconnection, because these two parts are disconnected, then it's a bit tricky. Even when we go to the Einstein frame, for example, then it's a point that do we want to be continuous or not? I mean, because
well, it's all, I would say it's quite likely that in theory it would give you continuity rather than it being sharp. If one tried to construct it, because otherwise you would be ordering the world crit to the universe and saying, and mandating it. So if you make it out of the field theory, then you will get some kind of transition.
maybe yes. I know that we did some assumption here, because if from, for example, here you can say from the UberGravity part, this critical density is just one approximation. So maybe the original model, this real UberGravity model, that complicated model, maybe it gives you a more smooth transition from this part to that part, maybe. But for simplicity here, we just go for this discontinuous scenario.
Well, you get much the same phenomenon with a, one of the regular types of gravity that you get. It's a very, very similar situation because it's effectively a low crit above in the neighborhood of that, and whether or not screening can be spread over a larger scale, or it's a short distance scale where you transition. And in your case, the transition is an absolute sharp transition.
Yes.
So is there a way to understand how this sharp transition emerges? Because in your assumption, you didn't assume anything sharp.
Yes, it is. Mathematically, it is possible actually. At r bar equals 1, you get 1. Agree? Because here it's 1, so we have this sum over e to the minus beta and divided by e to the minus beta. Okay. So here it's always 1. But for a smaller r bar, smaller than 1, this term is going to 0. So numerator going to 0, to a finite value, but denominator going to infinity. So for r bar smaller than 1, you always, asymptotically, you go to 0. So if n goes to infinity, then this fraction going to 0.
Average is dominated by large n part, and the large n part either
Yes.
converges or diverges when we go over that. When the average is dominated by large n all the time.
Sorry?
What you're saying is that this average is always dominated by the large n. Right? When that thing is smaller than 1, then large n is 0, so the average is 0. That thing is bigger than 1 and large n is large, so you get large effect.
No. When r is large, this factor is larger. So yeah, that one is going to 0 more rapidly for larger n's. Yes, please.
So what's the motivation for thinking that the real universe should be close to this ensemble average?
The motivation for me was the first question, that why, if I can, I mean, I do theory modified gravity, and then this one is a question for me. Why nature picked the GR? So I need a way. I don't say that this one is the correct way to think about that, but I want to answer to this question: why GR is unique, or what is the unique gravity model? In this way, I am trying to say that there is a scenario that gives you a unique model, independent of your first choice of models. Because as I said, this property is universal for all f of r models, analytic f of r models.
I think the philosophy is that it's a combination of theoretical prior, which is given a probability distribution, and then data is being added on that as a likelihood in terms of some grand Bayesian analysis. And so in that context, you can talk about probabilistic means and variances around them. I think your point is well taken. This is all like model selection, and presumably there's a unique model as opposed to the distribution. Of course, there could be a distribution of models in different parts of the landscape, but the standard picture would be that the mean is a statistical concept, not a fundamental gravity concept.
There's simply more than model selection because the weight is not just a function of model, it's also a function of state.
Say that again?
It's more than the model selection because the probability is not just a function of model, it's also a function of state.
What do you mean by state?
Because when the curvature is high, the weight changes. It's assigning the weight probability to different.
No, but that's actually, a priori, you don't know anything about that. And so
Yeah.
it's only the data which is going to tell you whether there's a scale and a density like that. I mean, so it's the data which is selecting the possibility that that can be true or not. And if, for example, the critical density was so low that you could never get there, then you wouldn't be able to say anything, and yet it could still be there underlying the theory.
Yeah, but the thing is that for fixed critical density, the weight is assigning to different models, not only depend on the model, but also depend on the density. And the weight is assigning e to the minus density over the critical density.
You mean curvature? But here at this part, yeah.
And somehow that's providing I don't get that actually. That's providing some kind of prior model for the probability.
But usually when we say prior, we don't care about only the theory, we don't care about the state. When we say we have a prior of different theory, I like this theory better, I give it
No,
more
but
weight.
the critical density is a parameter of the theory.
But the density is a parameter of the state. And it's way clear about the density, not only the critical density.
I guess we should be a little bit. Do you mean R naught here?
That R bar is density over critical
But
density.
that's the way Bayesian analysis works. You get all the information about the theory which has been developed. That will have all of that developed R information in. In other words, Lagrangian is part of the underlying theoretical prior, what the evolution of, as you call it, states. It's like, just realization.
Yeah, but usually that is a separate step. Usually that weight is separable.
No, but you don't have to think about it that way, and this philosophy is not thinking about it that way.
Okay.
It's combining the two ways of looking at the situation, that there is an update from initial theory space into the observable space, and then the statement of what's allowed and what isn't allowed is being defined by the unification of the two things, the observations applied on the theory space.
Yeah, but usually at least from what I've seen before, the unification is separable. You can integrate over your prior first, and then you condition on your data later.
Yeah.
Here they have to be combined in one function.
I mean, for me, it's a way that I should think about this Bayesian prior. Maybe it is a good way to think about the idea. But I mean, you can ask why this kind of probability. It's a question. I mean, and for me, it's one. Okay, maybe I didn't say in the last slide in my conclusion that the remaining questions for me in the UberGravity, in the theory side, is how I should define probabilities in a more fundamental way. Because, for example, you could go, I went for e to the minus beta Lagrangian. You could say I'm going for e to the minus beta Lagrangian square. So I have some motivations from from quantum field theory, from statistical mechanics, but it was just a matter of choice. So.
Any other questions? Well, thank you.